Thanks for coming, guys. Is this session I'm hosting is sodium ion debunking the myths. So although I'm the CEO and co-founder of UNIGRID Battery, a sodium ion battery company, I don't want to talk about UNIGRID today. Instead, I want to make it an open forum discussion about sodium ion batteries in general. I will not be talking about our technology, our value propositions, or anything about ours because I don't want this to be an ad. I personally hate ads. I have 4 different ad blockers on all my browsers. So I rather this be a discussion. And I've also prepared polls. Okay, let me talk about this. So to host this session, to prepare it, I decided to collect a number of topics from social media. And I also asked ChatGPT, hey, what are the commonly discussed claims, points of debate, or what are the misunderstandings about sodium ion, which I compiled a list here. And the first 6 are the most common ones. They are about technology, manufacturing, commercial adoption. Of course, there are many others that we can get to if we have time. And I would also like to hear from you if there is anything we missed. So I have a bad habit of monologuing to myself. So if anybody has any thoughts, opinion, please jump in and share. So to engage everyone in the audience, I have prepared a series of polls. So I'm going to give everyone a little bit of homework. So there'll be one poll survey question per topic for you to respond to when the first topic is posed. And then we'll see what everybody thinks before we jump into the discussion. So let's start into it. So we'll go in sequence. So the first one is about sodium ion battery and the energy density debate. So the question here is, oh my God, how do I get the poll up? Let me see. Oh, okay, yeah. So I'm gonna post my first question now. You should see the question pop up if nothing goes wrong. So the question is, sodium ion batteries have lower energy densities than lithium ion. And there's 3 choices, and none of them are right or wrong. I just want to seek opinions, right? So you have agree with the statement, disagree with the statement, not sure. Nothing is right or wrong. So please, input your answers. Wow, lots of high concentration of polls in one. So I'm going to end it in 5 seconds. Submit it if you have thoughts. Okay, I'm going to end it right now, and I'm going to share the results. Okay, so if you can see, the vast majority of folks in this audience selected agree that sodium ion batteries have a lower energy density than lithium ion. Some disagree, some are not sure, but to share some color on this, I'd like to pull out a figure from last year's battery report, which is this figure here. So this figure is a summary report comparing the specific energy density, so this watt-hour per kg by weight, how heavy something is, and the volumetric energy density, watt-hours per liter, or how much space something takes up. Let me walk you through this plot. So there's a few aspects to this plot. The round circles mean that so every data point here is a hyperlink to a commercial data sheet. So every data point here you see is a commercially available cell that you can buy online right now from a company. So you can go into the battery report, click it to get the details about it. But we worked hard to consolidate all the different data points we can find online. So none of them are projected, none of them are in R&D. Everything you can buy now. So the circle ones are cylindrical batteries, different sizes, 2670, 18650, 32140, whatever. The square ones are your prismatic cells, and triangle ones are everything else. Some pouches, some interesting shapes and sizes. The yellow ones are your polyanion technologies. So I'm talking about your NVPs, your NVPFs, your NFPPs. And the black ones are your layered oxide technologies. And the blue ones are the symmetric Persian blues. So there aren't many Persian blue technologies out there, and couldn't find a single one other than Natron. So you don't see any others here, so let's focus on the other 2. So the polyanion chemistries are concentrated here. They have specific energy density in that range, and volumetric energy density in this range. But it's quite clear that they are significantly different from the layered oxide chemistries, which are your nickel containing, copper containing, and NFMOs and stuff like that. But what's surprising is when we put LFP on this plot. So when we consolidate what the state-of-the-art LFP, you look at the BYD blade battery, you look at the CATL prismatic, you look at the highest energy density 32s, the 2170s, and even the 18650s. You can see that by looking at specific energy density, a lot of claims of sodium ion are not that far from LFP. And some of them are already encroaching on where LFP is. And that's where a lot of the news reports focus on watt-hours per kg. But what's often not reported is the watt-hours per liter point, where you can see a stark difference, right? Some of them are even, some of the polyanion chemistries are less than half the volumetric energy density of LFP. So I would say, at least with today's data sets, sodium ion in general does have a significantly lower energy density than lithium ion. There's a lot of work being done to improve this, but if we, just simply draw from commercial products today, this is the, outcome we have. I think there's a good point to start to see if anyone has any input or points they want to share. Otherwise, if not, I will jump to the next topic.
Wouldn't a NMC chemistry be far to the?
Oh yeah. NMC is probably outside of this plot.
Okay.
NMCs are in the 600 to 900, and some of your, I'd say, high silicon NMCs are close to 1,000 watt-hours per liter. But I think in general, most stakeholders don't really compare sodium ion with NMCs. They completely different application altogether. LFP is a common comparison metric.
So is the difference because of
Sorry, Peter, you got frozen.
I was just wondering is it because of sodium's relative new compared to how long lithium has been worked on? Yeah, or is it?
I think if all things are equal, that means at the chemistry level, if you make everything equal, sodium is, after all, higher in molecular mass than lithium. So if you take the same amount of energy, you divide it by a bigger mass, then your energy per mass is going to be lower. Does that make sense? Right. So that answers this question. But this one is mysterious, the watt-hour per liter point. And that's often associated with the anode, because sodium-ion batteries don't use graphite anodes. They use hard carbon anodes. And hard carbon anodes are very fluffy. They take up a lot of space. In fact, 60% of the space in sodium-ion battery is just carbon. So, that's kind of like my wife's bed, 60% of it is pillows. So you can think of it like that.
Thank you.
Yeah, so we want to try if we want to boost the energy density of sodium ion, we really need to do something about the anode. Of course, cathode, there are improvements as well, and there's stuff to be done there, but it's really at the early stages, like you said, and things are only going to get better. I see there's some questions in the comment list. Okay. The questions in the chat, maybe we'll talk about it at the end because they are kind of more general, not specific to this. I do want to get a post out for the other topics so that we can get everyone's view on this.
So maybe if I'm allowed a quick, go ahead, Phil.
Yeah, just a quick opinion gauge here. So, lithium had developed over time. So the volumetric energy, anyone who's been doing it long enough, which is not me, in summary, would you say that there's possibility that the volumetric energy is just low because it hasn't developed enough yet? And what sort of time frame would you expect given the LFP story?
Both are true. I would say I would agree. I wouldn't say true. I would say I would agree. So sodium really only kicked off commercially, I'd say, in the last 4 years or so, whereas lithium has had 30, 40 years of work done. and it is improving at a rapid rate. So sodium got from probably this region to here in the last 4 years. It won't be surprising if sodium is here in the next 4 years. But that also assumes that lithium doesn't continuously improve. And
Yeah.
we see a lot of innovations in LMFP, manganese dope, lithium.
It could be an interesting study at the rate of improvement per year of lithium to look back. Anyway, that's
yeah,
that's a side topic. But yeah, that was good, just a good insight. Thanks.
Yeah, go ahead.
Ian Gallo, Iveco Group. I mean, it's a question similar to the one in the chat from Michael. Will you be addressing maybe in a later slide the durability, the life expectancy of those cells?
Cycle life, I think we have one topic. Let me see if it's on the list. Yes, we have one there, but I'm not sure if we have time to get to that. I hope so.
Yeah, then let's go ahead. Hopefully we
Okay.
can get there and you can answer the question from the chat.
Okay. So next question is about safety. So let me launch the Q&A. So the question is, sodium ion is safer than lithium ion. Agree, disagree, or it depends?
This is Ahmad Pisaran. I have a question.
Yes, go ahead.
When you say lithium-ion batteries, I think it's as you know, there's many flavors of it, so it's kind of difficult to say which one you have in mind. So is it you're comparing with iron phosphate or NMC or NCA? What I mean, it's very challenging to say yes or no or answer that. So can you clarify that? What are you talking about? Which lithium-ion battery?
Right. Unfortunately, I cannot clarify it because there are also many flavors about sodium ion. So in lithium ion, you have your LTO, LFP, NMC, LCOs, and sodium ion, you have even more versions. So I think of it more as in general. I think if one would want to think about the general lithium ion, we can assume it's LFP.
Okay, thank you.
Yeah. Well, thanks for your responses. Another interesting set. I'm going to end it in 3 seconds. And I'll share the results. Okay, you can see the vast majority do agree. I'm surprised, actually. I thought more would disagree, and many put depends as well. My personal opinion is it depends. So to answer this, I decided to share 2 third-party testing, one from Sandia National Labs and another from US Naval Laboratory that will pop up later. So this study was a very interesting one because they are the only group who compared a true apples-to-apples comparison between a commercial sodium-ion battery and a lithium-ion battery. Now, when you want to compare safety properties of 2 things, you need 2 properties to match. One, you need the energy densities or the capacities to match. And 2, you need the form factors to match. Now, because there's no 2 chemistry with the exact same energy density, you will never get both to be the same. One will always be smaller, lighter, or if you force them to be the same shape, one will always have a higher capacity. But what these guys did was they took a commercial sodium-ion battery and they deliberately built a lithium-ion battery with lower energy density to match the sodium-ion capacity. So we end up having a very nice apples-to-apples comparison. So they have a 1.5 Ah sodium-ion cell and a 1.5 hour lithium NMC cell. And they basically did a barbecue test. So they put the battery in a heated chamber and gradually heat it up at a steady rate. And almost at the same point, at about 250 Celsius or so, thermal runaway occurred. And we saw a temperature spike. The amount of heat release was nearly the same. The point where the heat release was nearly the same. The rate at which temperature rise was also nearly the same. And the conclusion from that study was that for this specific chemistry, nickel-containing sodium ion was as safe or as dangerous as nickel-containing lithium ion. Now, what about other chemistries? Another very nice study that was also recently released was from Rachel Carter's group at US Naval Labs. So here they did a similar barbecue safety test on lithium NCA, lithium LFP, and a bunch of different sodium-ion chemistries. Let me talk about the lithium one first. So the lithium NCA one was the most explosive. The the temperature, at around 150 Celsius or so, the separator melt and the temperature rate skyrocketed to 7,000 degrees a minute. So that's really, really hot. Whereas the LFP one was very mild. It was only 7.2 degrees a minute. So this is the gray one, the LFP cell. They define this line as the thermal runaway point, 1 degree a minute. It's arbitrary, but it's just a general guideline. So the conclusion was that both lithium-ion batteries did undergo thermal runaway. Subsequently, they also obtained a sodium polyanion chemistry. This is the vanadium phosphate doped with fluorine, obtained from Tiamat batteries in France. And when they did the same test on it, it hardly had any heat generated at all. And the temperature rise rate was extremely low. It's not even 1 degree a minute. So it was concluded that this polyanion did not undergo thermal runaway, which is really exciting. However, they also did declare that the energy density of this cell is very low. It had only about 0.6, 0.7 M-hours per cell, where the NCA had more than 3 M-hours. So this is just something to take note. The next two cells they got were nickel-containing lead oxides, and both also had big thermal runaway events, just like we saw in the previous case. And the last one was a Persian blue chemistry. This was Persian blue or Persian white, and basically there was also no thermal runaway with this chemistry. But an interesting thing that I didn't show here was that they found a lot of hydrogen cyanide being evolved from this. So although there's no fire safety risk, there was a toxic gas risk. So the joke is that how would you like to die? Yeah, but I mean, basically my point of showing these two interesting studies was that whether sodium ion is safer than lithium ion or vice versa depends on which chemistry we were looking at, and depends on the test conditions and what we are measuring for. Yeah. Phil, did you have thoughts on this?
No, not really. I think it's I sell NMC, obviously LFP is very popular too. And it's always LFP is, always talked about being safer and everything. So, sometimes you have to understand, like you said, whether it's the fire or the gases that are emitted, what's going to be the problem. And
Yes.
when you think about a fork truck in a factory,
yes.
if you taint the whole factory with a poisonous gas, probably could even be more disruptive than a fire on a fork truck. But anyway.
Right. Yeah, the gas compositions is another thing that is often missed. And the gas absolute volume is another thing that's also often missed.
Yeah.
So in LFP, often fire is small, but the hydrogen gas release is very copious. So unless it's vented properly in an enclosed environment, it can cause explosions. And it's something that's often not captured in a lot of these reports.
Yeah. The fork truck industry is all LFP, mostly based on safety and cost, I guess. But safety has been the big driver of this.
Right.
So yeah. Anyway.
Okay. Yeah. Thanks for the input. I'll move on to the next one, unless anyone has additional thoughts. Okay, I'm going to release the next question. So this poll is, sodium ion can be manufactured on lithium ion manufacturing lines. Assume no changes at all. You can put your sodium materials on a lithium line, and it's going to spew out batteries in the same form factor. Well, interesting results. Very controversial. Okay, I'm going to end the poll in 3 seconds. 2, 1, and okay, I'm going to share the results. Okay, you can see it's really cool. It's an interesting split. Almost one third for all. About I guess 1/3 of us agreed, disagreed, and one said it depends. So to help answer this, I've decided to take another slide from the battery report. I'm plagiarizing them quite a bit, but to be fair, I did prepare the slides. So this is a study by Professor Martin Winter's group, and they compared the manufacturing protocols of various chemistries, next generation battery technologies, compared with lithium ion. So This black one here is a lithium-ion battery process. It tells you that you need to start from mixing, coating, calendaring, slitting, blah, 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 blah. And everything that is in gray was reported as a lithium-ion or identical production step. And everything that is in orange is a new step. So for example, LSB is lithium sulfur battery. So when you have lithium sulfur or solid state battery, whether it's sulfide or oxide, there is an additional step of extruding, calendaring the lithium metal foil. You need to you need to remove the native oxide layer. You need to laminate it. There are extra mixing steps for the solid state battery electrolyte, and the additional steps to do so. So in this article, they explain that a lot of next generation technologies like these mentioned here are plagued by a lack of existing infrastructure to scale this. And it was fortunate that sodium-ion batteries could have identical processes to lithium-ion batteries, which is partly the reason why we are seeing it being commercialized so quickly, because there was no need to change a lot of the infrastructure that goes into it. Now, I want to address the depends part, right? There's one caveat that is often also not reflected, which is that a lot of sodium-ion battery materials are far more moisture sensitive than lithium-ion battery materials like LFP. So although LFP battery lines have a certain dew point control in dry process, certain ppm levels of moisture control in the slurries and many other aspects, sodium-ion batteries may need to be stricter. And that's often that's one aspect of why it cannot be immediately transferred unless certain upgrades or unless certain compliance is ensured. Another aspect is also the concept of throughput. For the same 10 gigawatt hour factory and that produces lithium-ion batteries, if your energy density of the sodium-ion battery is half of lithium-ion, I'm talking about volumetric energy density, because production is done by volume, right? You do it by units, not by weight. That means that your 10 gigawatt hour factory becomes a 5 gigawatt hour sodium-ion battery factory, right? And it's the concept of throughput. So that means your OPEX cost per unit doubles. This is part of the reason why energy density is still important and something that we need to continuously work on. Yeah, so I hope this help answer some of the points about manufacturing. But in general, I'd say that although it's not a one-to-one duplicate, it is a lot easier to use a lithium-ion manufacturing line to produce sodium-ion than to produce other types of next-generation chemistries. Okay, I'm going to stop sharing this. And let's go to the next point. Critical materials. So this question let me launch this poll. Okay, launched. Right, so the question is that sodium ion does not use any critical materials. Critical materials, let me define it, are referring to 4 things based on the DOE definition, which is lithium, cobalt, nickel, and copper. So the sodium ion does not use any of these 4 critical materials. Okay, awesome. Lots of answers coming in. I'm going to end it in 3 seconds. And poll, share results. Okay, I see that the vast majority disagree. So meaning to say sodium ion does indeed use critical materials, at least some of it. Once again, I'm going to pull out another slide from the battery report. And this was prepared by Tyler from Mana Battery. So this table summarizes all the common cathode and anode materials used. You can see that in the list of cathodes, there are indeed critical materials in there. A number of very commonly used lead oxide materials, like the NFM material, do use a significant amount of nickel. Some other chemistries use a significant amount of copper. And it seems like most of the lead oxides cannot escape this. Even in polyanion, there's also a number that use vanadium. And vanadium, although it's not amongst this list of 4, it is still, it is only not amongst this list of 4 because it's not used in lithium-ion batteries. But it can also be regarded as a critical material because it is fairly expensive. It's only available in a few places. Yes, it's fairly abundant, but it can still create problems with supply chain. So this is something that still needs to be resolved. There are opportunities to eliminate critical materials entirely. As you can see, there are some materials here that do not use any of this four nor vanadium. In the polyanion world, there are also various polyanion chemistries that don't use any, they're based on iron. So you have your iron pyrophosphate chemistry, iron sulfate chemistries too. And these are some of the new latest developments that are being worked on, which are quite exciting. Okay, moving to the next one. Next is cost. Okay, oh, okay. This is I have some bars that I left there. This is I'll say the most spicy one to talk about. So I'm gonna launch the poll. So the question is, sodium ion is cheaper than lithium ion. I put a fourth option there because I know there are die-hard lithium fans here. And wow, okay. Yeah. So the first option is agree, sodium ion is cheaper than lithium ion. Second is disagree, it's not cheaper. The third is disagree today, it could be cheaper in future. And the fourth is it will never, ever be cheaper than lithium ion. Okay, I'm going to end it in 3 seconds. And poll, share results. Okay, I'm going to spend a bit more time on this one because there are a lot of controversial points here. So you can see that the vast majority disagree that sodium ion is cheaper today. It could be possible in future. Some agree that it's already cheaper. And there's a group who say that it will never be cheaper than lithium ion. Thank you all for your opinions. But I'm going to use a few helpful graphs here. So these are tables I've made because there are no good references online, so I just had to do it myself. The first is a calculated cost of lithium LFP from prices I can get in the wholesale market. So this is an oversimplified way of calculating cost. There are a lot of flaws with this, but for the sake of today's talk, I'm just going to create a simplified version. How this is calculated is I take 1 kilowatt hour of batteries, I divide them by the operating voltage, which is 3.2 for lithium ion. I know the number of amp hours. Because I know the number of amp hours, I know how many grams of cathode I need. I know how many grams of anode I need. I know the typical area loading. Therefore, I know how many meters square of separator I need, how many meters square of current collectors I need, and I populate them here. So it means that for every kilowatt hour of lithium ion phosphate, I need almost 1 kilogram of graphite, almost 2 kilograms of LFP, so on and so forth. To find the cost per unit of this, I go to this website, this IC Battery. So IC Battery is the Chinese government wholesale reported prices of, I don't know whether it's state government or not, but it's a helpful website that gives you all the prevailing prices of components of the lithium-ion battery world. And they tell you the market average, the last month's average, and stuff like that. So every number here is last month's average. So last month's average for graphite per kilogram in China is about $3.50. For LFP, it's about $4.50. For electrolytes, about $3, so on and so forth. I took this, multiplied by this, I get the bill of material costs. This is the bill of material costs. I apply a 25% cost factor, so I assume that the cost of producing a cell is about 25%, which is not far from most reports. And I got to this final number. So based on this very flawed method of calculation, I get the cost of production before any packaging, before any transport, before anything else. It's about $27.50 per kilowatt hour for LFP production, which I think is reasonable considering that we see reports of CATL and BYD selling LFP batteries for $30 to $40 per kilowatt hour. So if we take this number, we add some margins, we add some additional costs for overhead and stuff like that, which, it's not far to say that we should get to $30 to $40 per kilowatt hour. And we also see the system level cost today are in the 60 to 70 range, right? So now let's try this exact same exercise again for sodium ion. Okay, this is another table from sodium ion. So how I calculate this cost is I kept everything else the same. So separators will be the same in lithium ion. Aluminum foil is going to be the same. We don't have copper foil in lithium ion, so the amount of aluminum foil simply doubles. Carbon additives are the same, binders are the same. But to get the prices of the anode, cathode, and electrolyte, we go to the vendors and ask them, hey, if I'm going to buy a ton of hard carbon, what's your quote? And that's about $4. A ton of cathode is about $5, and a ton of electrolyte is about $8. So they are all still a good ways higher than the lithium version, but these are, of course, much lower volume. We did the same BOM calculation, but this time I applied a manufacturing cost factor of 2/3 or 66%. Why I chose this number is because today's quotes for cell level prices of sodium ion is about $80 to $90 per kilowatt hour. That's a good 2 to 3 times of LFP today. And I did the back calculation to find that it's about 2/3, and I don't think that's very far away. So today, the best we can do for sodium ion is roughly here. Now, why is the cost factor so high? I asked the cell factories the same question, and they said simply that they are utilizing a very small percentage of the factory. So a 10 gigawatt hour factory with sodium ion produced at 100 megawatt hour, which is very large, it's only 1% of the factory production output. So they complete the entire sodium production run in 3 days. And then they have to shut down for a week or two to do cleaning, to do shift change before they run, lithium ion again. So this causes a lot of high overhead, a lot of high turnover, and that's why manufacturing cost factor is still high. Now, let's simulate a scenario where in future, all this costs, because of scale, can come down by at least half, right? I don't think it's a stretch to imagine that hard carbon cost can be half because the cost of hard carbon precursors are potentially cheaper than synthetic graphite. So here we're looking about $2. Likewise, cathode, because there's no lithium in there, there's possibly no critical materials in there, it could be $2.50, considering that lithium containing LFP is $2.50. And electrolyte, half of $8 is still more than the lithium electrolyte, but just for simplicity's sake, we kept it the same. And let's assume the manufacturing cost factor for sodium ion can reach the same levels as lithium ion. Now you can see that if these conditions are met, if anode cathode electrolyte costs half from what it is today due to scale, and if manufacturing scale and cost factor matches LFP, you can see when the numbers of sodium ion will start to become competitive with lithium ion. So I'd say to a lot who are skeptical, I agree if these numbers are never reached, but a lot of people also believe that the LFP numbers wouldn't have been reached 10 years ago. 10 years ago, LFP was lower energy density than NMC, was lower scale, higher cost, and it took time to get there. So I cannot predict when this will occur. It could be 5 years, 10 years, 20 years. Not even sure in our lifetime, but if it were ever to occur, this will be the conditions that need to be met. I think it's a good time to stop to collect thoughts and address angry comments if there are any.
Yeah, I just want to say thank you because I have to leave to another call.
Okay.
But yeah, thanks a lot. I guess we can get the recordings. First time I've joined this call, so
yeah.
I guess.
Thanks, Phil, for joining. Nonetheless, I have one more slide, then I'll go into the Q&A before we talk about these other topics. Yeah. So the last slide is about applications. I'm going to launch the poll. Okay, so the question is, sodium ion primarily targets ESS rather than EVs. I really appreciate the active participation with the audience, so thank you all for responding to this poll. I half expected this to be a monologue, so I'm grateful. Okay, I'm going to close this in 3 seconds. Okay, sharing results. All right, so I see that vast majority do agree that sodium-ion primarily targets ESS rather than EVs. To talk about this, I'm going to just share some reports. Interestingly, China is doing both. Today, there are about 3 to 4 mega sites of BESS deployments using sodium-ion. And there are also 3 to 4 car models powered by sodium-ion on the roads there. Unfortunately, we don't have enough data points from the rest of the world. It seems like nobody else is doing it yet. So it is still an intense debate on whether either are possible. And this debate often centers around the energy density downsides of sodium-ion battery and the cost downsides of sodium-ion battery, especially today, where costs are still much higher. But I think that the real question is, beyond cost and energy density, are there other value propositions that could justify use of sodium-ion in these applications or their sub-applications? Things like improved safety, low or high temperature operation, high power capabilities. To give an example, today, when we install any battery for our homes, for our offices, for our factories, we can only put it outdoors or in a garage, right, behind a fireproof wall. We can't put it in a high-rise building. We can't put it in our bedroom. There are restrictions due to the reality of the safety limits of lithium-ion. But if sodium-ion can overcome these limits, then perhaps safety becomes a more important value proposition than energy density and cost, and will justify it simply because you cannot do it with lithium-ion. Likewise, for low temperature operation, there are some applications in the world that frequently undergo low temperature, either at high altitude or near the poles. And that's probably where the low temperature capability would justify deployment over energy density and cost. Now, if you look at the trend of what I'm trying to get to here, is that sodium-ion do not necessarily need to compete or replace LFP in these markets. And that's also because LFP did not replace NMC or lead acid or alkaline batteries. The new technology has always, in history, always served new applications, enabled new markets that existing technology hasn't. So I'd say, both ESS and EVs do have opportunities for sodium-ion. It just may not be in the exact same type of deployment that we imagine and see here today. Both the ESS and EV markets are very broad markets. There are many sub-markets within the ESS. You got behind the meter, front of meter, short duration, long duration, middle duration. You have front of meter, you have like a commercial deployments, private deployments, utility scale deployments. Likewise for EVs, you have everything from a micro mobility scooter all the way to the giant trucks and everything in between. So I'm sure there are pockets of applications where one would be more suited over the other. Okay, yeah, thanks for sitting through this first 6 slides. I'm going to go to the Q&A now. Let me see if I can open the chat. Okay. Wow, so many questions. Okay, let's see if we have time to go through them. Okay, first one is from Peter. He asked, how does sodium ion compare to silicon alternative? There's another talk at this forum. I'm not sure how to answer the question because I'm not in that talk, so I'm not sure what they're talking about. But I would say silicon in general, I believe, serves high energy applications. They are not designed to go for 5,000, 10,000 cycle life. So we may not even be talking about the same application here. Anything who needs extremely high energy density, silicon, lithium metal, lithium sulfur will be the way to go. If energy density is your top priority, probably sodium ion is not the best choice. Next one is, any comments about bedrock shutting down because they claim it no longer make economic sense? I read the article. I think there's a lot of controversies about that. Not sure if this is the best place to discuss this. Adam, if you want to talk about it privately, I'm happy to set up something separately. But in every industry, with every batch of startups, some will succeed, some will fail, some will actively choose to stop work, and some will keep pursuing. So I guess it's just part of the trend. Yeah. Next question is from Michael Perron. Curious on your take on the Stanford study noting problems with degradation of sodium-ion batteries faster than LFP. I don't know this study, but from our own results, so as a company, we buy a lot of LFP cells from different commercial, and we compare them with our own batteries and also commercial sodium-ion batteries. We found that LFP is great within the Goldilocks zone. So LFP is like a little baby. You just keep it never too hot, never too cold, never over discharged, never charge too fast. It will run very well. Sodium ion is more robust. So when you test sodium ion and LFP at an elevated temperature, for example, at 60 degrees Celsius, you will see LFP, crashing really quickly. But sodium ion, maintains strong. It's not as good as room temperature, but it still gives you decent thousands of cycles, even at high temperature. Likewise at low temperature too. Calendar life is also pretty good with sodium ion than LFP. So I'd say that at the Goldilocks zone, if you keep an air conditioner, thermal management, all your systems are good to go, LFP will win. But if you are deploying it in places where it needs to take a beating, it looks like sodium ion can do a little bit better. The next question is from Clint. Lithium is lower energy density and has greater electronegativity than sodium. Does that mean lithium-based batteries have an advantage in terms of energy density? By default, yes. I mean, the element is lighter. It's always going to have a easier time. Likewise, it's not only that, the reduction potential of sodium is lower than lithium by 0.3 volts. So you already lose something there. And high voltage sodium cathodes seem to be struggling a lot. So it's very unlikely we'll get a very high voltage sodium ion full cell. That's why I think that sodium ion batteries should work on improving energy density, but they shouldn't try to beat lithium. That shouldn't be the benchmark. Next question is from Julie Jia. She said, I would assume a lot of learnings we have from lithium ion are being applied to sodium ion. I would not expect the rate of improvement to be the same. That is already very obviously seen in the last few years. We've seen sodium ion basically not repeat a lot of the same mistakes lithium ion did, especially in manufacturing. We don't have to. So, for example, when I asked the sodium ion producers in China, say, are you attempting to do dry electrode manufacturing yet? And they said, let's let the lithium guys solve it first, and we'll just use it once they figure it out. And I think that's a good approach to take. Don't reinvent the wheel. Learn from past mistakes and try to, do it more efficiently. Next one is Timothy. He wants to talk about cycle life. So cycle life is another very controversial topic because there is no data about this. Most of the sodium ion cells haven't had enough time to cycle that long. And often when they cycle sufficiently enough, new versions come out and you have to restart the cycle test again. It's not like a commoditized LFP where the technology doesn't change for 10 years and you can get started today and you can get a result 5 years from now. But sodium ion, every 3 months you get a new version. So it's really hard to compare cycle life. Currently, we only have extrapolated data. And the extrapolated data looks really good. So if I can cycle a sodium ion battery for 1,000 cycles, and I take the average kilowatt efficiency and I project it, I tend to get more than 10,000 cycles at 100% level of discharge. But of course, this is an extrapolation. Nobody believes extrapolation all the way. So we just need to wait to collect more of these cycle numbers. Next is from Ahmad. He talked about calendar life. I mentioned it already, so I'm going to skip that. Sid made a comment that Natron Energy uses Persian Blue and just built their Gigafactory. Just a comment, so I'm going to skip that too. Next is from Phil. He's interested to read reports and studies on the dangers of thermal events on different chemistries, specifically reports that also address gas ejection implications. If anyone has a good source. So Phil, I would recommend reading those two papers I talked about, the one from Sandia National Lab and from US Naval Laboratories. That's a good place to start. But we expect a lot more of these reports coming out. Now we only have cell level reports. Module pack level system reports should come in the next 6 to 12 months or so. If not from US teams, probably from Chinese teams. Sydney asked about, do people worry about the toxicity of hexavalent chromium? So chromium 6 plus is one of the most toxic materials. It is a big concern, and one of the reasons why it was US used to produce chromium, but it was moved offshore. Yeah, so hexavalent chromium should never be used. Most of the studies that use sodium chromium oxide based cathode materials use trivalent chromium, and in the operation process it doesn't reach the hexavalent state. In fact, it's very difficult to achieve the hexavalent state. You basically have to synthesize it to achieve that state. The nice thing about this cathode is it doesn't undergo thermal runaway, so it doesn't have this oxygen release point, heat release point. So hexavalent chromium should be avoided. And in fact, trivalent chromium is so safe, it's not even regarded as a hazardous material, such that the US Mint used to use it in our dollar bill, and that's why it's green in color. And trivalent chromium is also used in all steel products. So our fork and spoon, our pots and pan has chromium, and that's what makes it stainless, right? Yeah. Oh, thanks, Edmund, for clarifying. Yeah, IC Battery is a company who sells information. But I'm glad they offer the information for free. Environmental cost, important factor in risk mitigation. Yeah, so this one is very difficult to tackle because we don't know what sodium ion would be yet. What is the exact chemistry of sodium ion? Sodium ion chemistries are now like the Wild West, right? It's like lithium ion 30 years ago. There's so many different versions. Everybody believes theirs is the best, but inevitably it will filter and funnel down into your LFP, your NMC, your LTO. That takes time to occur. I have my own bets on which one will be the final 3 or 4, but until that happens, it's very difficult to do a life cycle analysis or to predict what needs to be recycled, right? Because we don't know what's going to be there. But there's one thing that I hope, which is that we move away from fluorine. Fluorinated electrolytes is a very challenging thing to handle for lithium ion, and I hope we don't repeat the same mistake for sodium ion. Unfortunately, we cannot really escape fluorine in lithium ion. Fluorine has a lot of positive benefits for SEI, for stability, for column efficiencies, but looks like fluorine is terrible for sodium ion. And I would encourage the electrolyte makers to start removing fluorine from your sodium ion electrolytes. Let's see. David mentioned that it took lithium ion decades to reach 90 kilowatt hours. I think he's referring to energy density. So Sid mentioned that Steer report from Stanford said that unless LFP cost stabilizes, sodium ion is unlikely to match LFP. Their report said that it's unlikely to match in this decade. So interestingly, they project that the sodium ion cost can only match LFP or go below LFP past 2030. I somewhat agree. I think that LFP cost is still going down. But when we think about it from first principles, right? If production is almost the same, then we really look at bill of materials. And lithium carbonate is made from sodium carbonate. So sodium carbonate is going to be a lot cheaper all the time, no matter how low prices lithium reaches. The raw materials of sodium is still lower. So I think it's inevitable as long as demand is there. If someday people don't want to buy sodium ion batteries anymore and we will never reach that scale, then yes, true, the LFP will always be the dominant technology of the day. Edmund asks why electrolyte for sodium batteries are so expensive. Simply, it's just not made enough yet. We're just making it in a couple of tons right now. It's all custom ordered. We can't even decide which electrolyte we want to make, which salt we want to use. So it takes time to reach that kind of scale. John Lim asks, are cathode materials for sodium-ion batteries more sensitive to moisture than the one for lithium-ion batteries? So far, it looks like so, especially the layered oxides. The layered oxides are far more sensitive than the ones for lithium-ion, at least from our own data sets. So they often need dry room temperatures with dew point of -40 or drier. That's not because the materials are intrinsically more sensitive, but I think they're just not as advanced yet. For example, sodium-ion cathodes are not yet coated, and many of them, the coatings have not been explored. We're not sure what the best coating is for sodium materials yet. They're just using the lithium coatings to apply the sodium cathodes. Their morphologies are not figured out yet. A lot of sodium cathodes are fragmented, broken secondary particles. They're not nice spheres yet. They're still figuring out if single crystal is the way to go or polycrystalline is the way to go. So I think the moisture sensitivity will only improve, but for now, it looks like it's still more moisture sensitive. So Luis here asks, how does sodium-ion battery compare to others in terms of cell aging? Oh, I mentioned this earlier. So sodium-ion batteries look pretty good to temperature aging. They hold its charge for a long time. They have pretty low self-discharge. And this is especially so for the lower nominal voltage batteries. So for example, those that operate in the 3-volt range. The 4-volt and above batteries still suffer from aging issues. But in general, it's pretty good. I don't see much issues with cell aging for that. Oh, thanks, Ahmad, for the comment. Let me see. Louisa asks also, is there a specific type of form factor that sodium-ion batteries especially work well with? I don't think so. Currently, sodium-ion batteries are just made in whatever form factors is convenient to make. So we go to the lithium-ion factories and say, hey, what form factors do you use? We'll do the same. Just take these materials, make it exactly the same. So we don't really want to customize anything special because it takes a lot of capex and a lot of unnecessary work. And a lot of the applications for sodium ion are not form factor sensitive either. A prismatic cell, whatever size, they'll take it. Cylindrical cell, most sizes, they'll take it as long as it's big enough. Sid mentioned, aren't cell level cost an imperfect comparison? One has to look at system level cost at EPC level that takes all the inputs and include safety, energy density and stuff like. Absolutely agree. Yeah. But it's just not. It's too difficult for me to compare things on the system level cost in this session, and every system is different too. Different system size have different consideration. Different deployment location have different consideration too. Cell level cost is just an oversimplified but flawed way to compare things. I'm going to skip Adam's comments about bedrock. We can talk about this separately. Siva mentioned, can this chemistry, silicon anode and sodium iron phosphate, have any potential? So it breaks my heart to say that sodium iron phosphate cannot work. It doesn't have a stable phase. So if you make sodium iron phosphate and you try to cycle it, you'll see 2 plateaus, not 1. So it undergoes a phase transition and it's not stable. So what innovators do is they remove a couple of moles of oxygen and the structure transformed from the olivine structure into the Nasicon structure, and that's where you get sodium iron pyrophosphate. That's the stable version of it. So that's how we end up with this polyanion chemistry. Now, it also breaks my heart that silicon anode doesn't work for sodium. So silicon is inert to sodium ion. It cannot store sodium. So the prevailing alloys for sodium ion batteries are other alloys like tin, antimony, lead, phosphorus, and a bunch of other candidates. So there are many teams working on those. We will see where those land up. But I think alloys have a better chance in sodium ion than lithium ion. Edmund asks, is NFP electrode very heavy? I'm assuming you're talking about NFPP, the pyrophosphate version. So it's not heavy, it just has a low capacity and low volumetric energy density. So the reversible capacity of NFPP is about 90 milliamp hours per gram, which is significantly less than a lot of layer oxides. It also has a terrible tap density. So its tap density is something like 0.6 or something like that. And after compaction is just under 2 grams per cc. So it takes up a lot of space. So for the same can, you actually get much less amp hours compared to many other chemistries. It's improving, and I'm interested to see where it goes in the next few years. Oh yeah, we got through all the questions. Yeah, thanks everyone. Yeah, okay, great. I'm going to go to my last slide to see if there's anything particularly specific anyone here is interested in that we can address. Otherwise, I think we kind of exceeded our time, right? Yeah, so if there's any topic here that anyone's particularly passionate about, we can talk about it. You can mention it in the chat or just unmute yourself to share. Otherwise,
Darren, I was actually a bit curious where you say shipping at 0% versus 0 volts. I guess, what do you mean by 0 volts? Do you mean like using sodium metal as anode and then you're just fully discharging to the sodium, or usually 0 volts is no bueno for batteries?
Yes. So that's actually a complicated question. So we know in lithium-ion batteries, you cannot ship at 0% or 0 volt, right? You always ship at 30%. And the technical reason for that is because of the copper foil. So copper dissolves into electrolyte, and if your cell voltage goes below a certain point, it will precipitate on both your electrodes, and that poisons the battery and cause your cell to die a lot quicker. That's why most lithium-ion batteries are shipped at 30% based on UN 38.3 requirements. Now, sodium-ion batteries have no copper foil. Both sides are aluminum foil, so you don't have this copper dissolution problem. So you are free to ship it at 0%. And some people ask, can I ship it at 0 volt? Right? We have tried it. It works, but there are consequences to it. We noticed that the sodium-ion batteries that are shipped or stored at 0 volts don't perform as well as those that are shipped or stored at 0%. But it's not because of the copper foil. What happened is post-formation, SEI and CEI is formed on both electrodes. And those are only stable within a certain electrochemical window. And if you leave that window by going to 0 volts, then they break down. So you basically reform the cell again when you cycle it after being stored at 0 volt. But 0% is not a problem. But most companies don't ship it at 0% because it's inconvenient, right? They like to ship it at 2% or 5% because when the customer receives it, they do a quick quality check. And if their voltages are all in the same range, they accept it. And if one is out of this range, there's a poor quality request for warranty and stuff like that. But when you ship batteries at 0%, the range is very large, right? Because of the double layer capacitance in all the electrodes. So just simply out of convenience, most sodium-ion companies ship it at some amount of charge that's low enough. Yeah, but don't do 0 volt, at least until new knowledge is discovered. Okay, hope that answers your question, Julia. Okay, David asked, interested. Oh, we talked about that already, David, so I won't talk about that again. James mentioned when you focus on safety aspects of sodium-based chemistry, have you benchmarked LTO? I'm not sure what TNO is, but LTO, yes, we have benchmarked in our own company. So we bought LTO batteries, we do the barbecue test on it, and you'll be very surprised. LTO is also has thermal runaway. And the reason is that LTO, although the anode is very safe, the cathode still uses NMC. And most people forget that. So it is the NMC in the LTO cell that undergoes thermal runaway, not the LTO itself. But LTO as a battery is safe because its energy density is low. So when there's not much energy to release, of course, it's going to be safer. But definitely LTO is robust technology. Edmund asks, what's the difference between 0% and 0 volt? So 0% just means there's no more charge, and 0 volts means you physically short the cell. So there is a benefit of doing 0%. So for example, if I'm shipping a ESS storage system, and that's connected to a high voltage system, let's say a 1200 volt string, even at 0%, it's 1000 volts or something like that. And that can be dangerous for operators. But if I can connect the wire to create a closed circuit to make it 0 volts, then it's become super safe to handle and ship. There are not going to be sparks. People who are not certified for high voltage systems can handle it and ship it. So that's one of the reasons why people wanted to explore 0 volt storage. So it's different from 0%, just to clarify. Yeah. Miku asked about getting a Calme IC battery. I don't know. You got to figure it out. I don't have one either. I just scroll down. My suggestion is to open it on Google Chrome, and you can press the translate option, and they'll give it to you in English. Seth asks, what are the system level savings in BSS enabled by reduced need for battery cell cooling? I don't know, because UNIGRID is a cell and pack company. We don't build systems. So we support customers who build these systems. They do give us some numbers, and they range a lot from 10 to 40%. It really depends on where it's being deployed. If the BSS is deployed in the desert where it gets really hot, then your cooling needs are tremendous. And guess where the energy for cooling comes from? It comes from the batteries itself. So the batteries are cooling its own heat generated from powering the cooling. Yeah, but anyway, I don't have a good answer for that. Hao Chuan asked, could you introduce more about the low temperature benefit of sodium-ion batteries? This is a long topic to discuss too. So sodium-ion batteries can do well at low temperatures up to negative 40 degrees Celsius, and we know lithium struggles anything below 0. Now, there is a common confusion here. Most people think that it can do low temperature because of sodium. It's nothing to do with sodium or lithium. It's all to do with the electrolyte. Because in lithium-ion batteries, you have to use graphite. You can't escape graphite. And graphite is a very difficult boyfriend or girlfriend. It only wants to eat at a few places. So you can only use a type of electrolyte component called ethylene carbonate with graphite. You cannot use anything else with graphite. Graphite will exfoliate if you use other types of solvents. So ethylene carbonate becomes very viscous once it gets a little chilly. So lithium-ion batteries cannot run well when it's cold. But in sodium-ion batteries, when you have no graphite, you use hard carbon, suddenly the options for all the different solvents open. You can pick ethers, you can pick esters, you can pick all kinds of other carbonates, and they all work well at low temperatures. So if we do a mental exercise, if you build a lithium-ion battery using hard carbon instead of graphite, you can also do low temperature performance. So yeah, low temperature is not related to lithium or sodium, it's related to electrolyte. Luisa asks,
ask a question here?
Yes, go ahead, man.
Yeah, sorry. Just for the open discussion topics, there's a like high temperature operation. Have you ever tried like the temperature above like 80 Celsius? I don't know the Fahrenheit, but
80 Celsius. Wow, okay. We didn't. We've only tested the 60. That's because that's the the temperature chamber limit of what we use. Most battery equipment makers don't offer 80 Celsius or below 40, negative 40 either. Will be interesting to try, but if you like, you can reach out to us. We'll send you a couple of cell samples. Oh, that applies to anyone in this chat too. If you want some sodium-ion batteries, send us an email. We're happy to send you a few samples of cylindrical batteries or whatever batteries you want, and feel free to test it and let me know the results you get. Okay, Lucia asked about commercial readiness at the last point. So this is a how to say debatable point. We are seeing tremendous commercial adoption of sodium ion in Asia, in China, in India, in Southeast Asia, even in Japan. There's a lot of interest of this. But in North America and Europe, the interest is a little more slower. The adoption rates are also slower. I'm not sure if it's because of tariffs or not, but there is growing interest, but it is already getting deployed in many parts of Asia. Yeah, so I hope to see similar trends happen here soon. Vinette asked about max C rates for sodium ion presently and likely in future. So sodium ion can do extremely high C rates, both in charge and discharge, and it's not related to sodium again. It's also this time it's related to the anode. So in lithium ion, most of your limitation or your challenge is about the graphite. Graphite is very good in a lot of things. It's just not the Ferrari of anodes. It takes lithium slower and releases lithium slower. And if you do it too fast, you can cause plating and nasty things to happen. But once you swap it out for hard carbon, suddenly everything moves at like lightning speed. That's why sodium ion is great for fast power or high power applications. Sydney asked for long duration potential. What do you mean for grid application? What do you consider long duration? Oh, that depends who you ask. So how we define long, short, and medium duration, everybody has their own opinion. But I think sodium ion is not ready for long duration. Long duration, short duration, and medium duration to me is exactly the same. It all depends on whether your levelized costs make sense, right? The longer your duration means you discharge over a longer period of time, which means you use your batteries less per year, which means there's less chance for you to make your money back. When it's short duration, you're charging and discharging many times a day, you're making a lot of margins. Your arbitrage income is very lucrative. So sodium ion has not reached the point where its cost can justify long duration yet. Lithium ion has not either. So I don't think long duration will be a target market for the sodium ion folks for a while. Okay, I'm going to skip the questions about the website account creation. Edmund asks, will there be I think you're talking about pre-sodiation. So pre-lithiation has been a common strategy for the lithium world to compensate for first cycle efficiency losses. Unfortunately, pre-sodiation is not practical. Anything to do with sodium metal is not practical. Sodium metal is too reactive, too unstable, and too dangerous to handle at the industrial scale. It is already hard enough to process and buy lithium foil. I don't think it's practical to process and buy sodium foil or potassium foil for that matter. So any kind of sodium pre-sodiation technologies cannot be based on sodium metal. You have to look at sacrificial salts, you have to look at other kinds of methods, but I'm not a fan of pre-sodiation. It's not an elegant technology. It's probably wiser to find other techniques to improve the first cycle efficiency. And most first cycle efficiencies are 90% and above already for very close to 90% for sodium ion battery. So it's not really a problem. Edmund asks, Edmund mentioned it's true. Chao Chuan asks, what about operating voltage range? Ooh, this is a long topic. Oh, how do I compress all these ideas? Sodium ion batteries have a notorious reputation for having a wide operating voltage range, right? Your most common sodium ion batteries, lead oxide, operates from 1.5 volts to 4.2 volts. That's more than three times the range, right? And it's a very slopey curve. And some of the others have narrower but still far wider than LFP. So what's the consequence of this? This means that it is no longer compatible with existing power electronics. Most of your power electronics are designed for lithium ion with a certain range. And to change the whole power electronic supply chain is going to be very challenging. So what a lot of system integrators of sodium ion do is simply they chop off. They chop the top and chop the bottom of the sodium ion operating range and just accept the middle, sacrificing capacity or sacrificing energy density. So for those in the audience working on sodium ion battery innovation, my appeal to you is please work on chemistries that give you a flatter voltage range, narrow voltage range, but longer capacity. Don't pursue high voltage and higher voltage, stretching the plateau to the moon. Yeah. So all your applications want a constant power output. Nobody wants a depreciating power output. So it's easy to just say, oh, the industry guys will take care of it. They are not going to do it. Everybody wants the lowest hanging fruit. Everybody wants the easiest way to deploy. Don't make it harder on your customer. Sydney mentioned if there's no sodium foil available, doesn't mean sodium solid state is not promising. It's the opposite. Because there is no sodium foil available, we now have to use anode-free. And anode-free has a much better chance of succeeding in both sodium solid state and sodium ion batteries. I believe that if any anode-free battery were to succeed, it's already very hard, but if any were to succeed, sodium ion will succeed first. There are very fundamental thermodynamic reasons why that's the case. And I can write a textbook on it, but I believe that's the case. But doesn't mean we're close to it. It's still a lot of work to do. Have we seen any application of sodium-ion batteries in the off-highway sector? Yes, a lot actually. So sodium-ion batteries are very popular in industrial vehicles. So I'm talking about forklifts, especially forklifts that operate in the warehouses, because you don't want a diesel generating forklift spewing gas, and most of them are lead acid powered. They don't last very long. So we have a customer that uses lead acid battery forklift, and they do half shift a day before they need to charge. But once they use sodium ion, it lasts 3 days. So they are quite happy about it. And forklifts need the weight too. So you're not that worried about energy density. And because it's operating in the warehouse, it needs to be safe. There's also the, vehicles that operate on the ports. They don't travel very far, but they need to move heavy loads. Vehicles that operate in airports, stuff that move your luggages, that push the planes back and forth. Farms too. Farming equipment are being electrified too. Construction equipment too. Things that move a lot of load, need high uptime. So those are, just new interesting applications to explore. John asked, if the cathode half cell for sodium-ion battery was not discharging properly, could you give me advice on what major problem they are? Oh, wow. Okay. I guess this is a lab question. Without seeing the curve, I can't judge, but I can give some general points for researchers starting to work on sodium-ion battery. Sodium-ion battery research is difficult to get into because it's not easy to even make a half cell. There are a lot of tricks there. For example, you can't buy sodium chips, right? The sodium chips are not easily available. So how do you make a half cell? You have to make the chip yourself. You have to buy the sodium ingot, cut it and roll it like pizza. And if you wait more than a few hours, it will just oxidize away. My advice is to consult someone who has made half cell before. You can't use the same separators as lithium too. Don't use the cell guard separator for half cell. Use the glass fiber. You can buy online. There's specific ways to prepare the electrodes too. Yeah, I'm sure there's someone in your circle who has made a sodium half cell before. Do reach out to them. Edmund asks, in China, many workshops are forced to use e-forklifts. No more gas smell inside workshops. Yeah, that's true. There are a lot of advancements in Asia about this, and that's really the sweet spot for sodium ion. Not that lithium ion cannot be used, but it's just a better fit. But then again, there are also different downsides that are being worked on. Okay, yeah, thank you all for the questions. It's been a pleasure to talk about this, almost a monologue. Yeah, thanks myself for the thoughts. I think it's a good place to stop. Feel free to send me an email or message me on LinkedIn if you have any other questions, or if you like a couple of sodium-ion batteries to just keep. And I thank you all for being here, answering all the questions, and hope to get to speak to you more in the future events. Yeah, thanks everyone for coming.